In follow-up with the previous video's assignment problems, we are going to make solutions to few problems, and further we are going to add some practice questions in this video. So let's see this question. In figure, there are two particles A and B, each of mass m. A is connected to ceiling by a light inextensible thread OA, and B is connected to A by a light inextensible thread AB. Initially, OB is vertical. System is released from rest. The initial accelerations of A and B are given. They are given as A1 and A2 respectively. Find the value of 5A1 by 2A2. So told that the threads are inextensible, and let us imagine if we release the system like this, how would they move? Definitely B is going to fall downward. A tends to fall downward, but the string OA, which is fixed at O, doesn't let it. So from beginning itself, A is constrained by it. So B will be falling downward under the influence of gravity because no tension forces are described in the strings, though the strings doesn't appear slacken. B will fall downward with an acceleration G. So let's represent for B, it's told the acceleration initially is for A2. A2 is G. And for A, as I don't know how the A is going to move, I'm just making as an assumption. Let horizontal and vertical components of the net acceleration of A would be, say, AX and AY. And we know this angle can be 37 degrees. And this angle also 37. And this angle is 53 degrees. So now along AB, the relative acceleration of A and B should be 0 because the string is inextensible. So for that, the component of acceleration of B along the rope along the string is, this angle is 37. A2 cos 37. This A2 cos 37 should match up with the acceleration of A along AB. So I'm writing along AB. So we can write G cos 37 equal to AX cos 53 AY cos 37. Cos 37 4 by 5 G. Cos 53 3 by 5 AX. Cos 37 4 by 5. So cancelling 5 on both sides, we got some relation. 4G is 3AX plus 4AY. This is one equation, but one more thing we can observe. You can just take along OA, as O is at rest, point O of the rope or the string is at rest. Point A also along the rope should have zero acceleration because along the rope, the relative acceleration for O and A of the inextensible thread should be zero. As O is having zero acceleration, A also should have the zero acceleration. For that, uh, we can say, acceleration AX component is AX cos 37 here, and AY cos 53 here. For relative acceleration along OA to be 0, for acceleration of A along OA to be 0, we can write that ax cos 37. Cos 37, we can write it as 4 by 5. Ay cos 53, 3 by 5. So we got a relation 4ax is 3ay. Now, using this equation and this relation, we can find what is ax and ay, by which we can get a1. Because the acceleration a1, we can write it as a1 is acceleration, initial acceleration of a, which is root of ax square plus ay square. We want a1, for which we will find ax and ay in terms of g. So let us substitute. First, I'll substitute ax. Ax is 3ay by 4. So therefore, 4g equal to 3 times, in the place of ax, I'll write 3ay by 4 plus 4ay. So this gives me 16g, 9ay, 16ay, that gives me 25ay. So ay is 16g by 25. If ay is that, then ax is what? Ax would be 3 by 4 times ay. So that gives me 12g by 5. So if I use this relation, I'll get a1, which would be root of ax is 12g by 25, and ay is 16g by 25, and that gives me 12 square is 144, 16 square 256. So totally I'll get 144 plus 256 is 400. So 20g by 25, that would give me 4g by 5. So I want 5a1 by 2a2. That makes 5 by 2 times a1. a1 is 4g by 5. a2 is g. So that gives me 2. So 2 is the answer for the problem. 2 is the answer for this question. Going to the next one. Now here, in this problem, particle P is initially at a distance d 16 meter from a fixed point O. The particle P moves with a velocity given by P 5 times P O cap plus 3 I cap, where P O cap is a unit vector from P to O at any time t. Initially, P O cap is perpendicular to I cap. Find the time in seconds, after which point P meets O. Initially, PO cap is perpendicular to I cap. I'm assuming some x and y axis. I'm assuming origin. PO cap is initially perpendicular to I cap. See, I cap is along x axis. So initially, PO cap is perpendicular. I'm expecting it to be on the y axis. And it's told that d is 16 meters. So initial position is 0 comma 16 for the particle, and it is told that always the velocity of the particle is such a way is 5 times unit vector, and always 3 I cap is there. So that means always a velocity along x-axis of 3 units, and always a velocity 5 times PO cap. So, like, initially the particle is here. Now, as time passes, because 3 I cap is pulling along, causing a displacement along x axis. Simultaneously, there is some velocity along, always directed towards origin at any instant of position of p. So maybe somewhere particle would be somewhere here. Let's assume. So at any instant, the particle has got a velocity of 3 units along x direction. This is x direction, and 5 units towards origin. Always. So 5 units towards origin and 3 units in the x direction. Maybe the particle would have come like this. Now let us say that the particle has traversed some angle theta over here. If I put a vertical at this new position of P, we can write this angle also theta. So let's assume that the particle's position vector with respect to this coordinate system be r. We can resolve this 5 into components. The component is phi sine theta towards left and phi cos theta vertically downward. We can write uh, in the x direction 3 minus 5 sine theta is the velocity at any instant along x direction. So 3 minus 5 sine theta into dt should be giving me dx. Let me integrate on both sides. We want the particle, when will it reach the origin? My initial x coordinate is 0, final x coordinate also 0. In what interval it will reach the origin is a question. 0 to t, let's say. The result of integration gives me 3t minus 5 times integral 0 to t sine theta dt, because I cannot integrate this because I don't have theta in terms of t, but on the right side I will have 0. So integral 0 to t sine theta dt gives me 3t by 5. And let me see along the radial distance r. So along this direction, uh, we got 5 for the particle velocity. The net velocity would be, as this angle is theta, this would be theta. So this is 90 minus theta. So that gives me 3 cos 90 minus theta is 3 sine theta. So along position vector, if I write the velocity along position vector, so position vector is changing, and along position vector, if I write 5 minus 3 sine theta is the velocity towards origin. 5 minus 3 sine theta into time interval will reduce the position vector, because I am choosing the position vector, velocity along position vector towards origin. So that gives me minus dr. So let me put integral on both sides. So initially r value is 16. Finally it should reach origin. So position vector value in magnitude is 0. This all should happen in the interval 0 to t. So this gives me integration 5t minus 3 times integral 0 to t sine theta dt, and on the right side I will have 16. So for the writing, we have 5t minus 3 times. We got integral sine theta dt as 3t by 5. If I substitute that, I would have 25t minus 9t gives me 16t by 5 equal to 16. Therefore, t would be 5 seconds. So the time interval after which the particle reaches the horizon would be 5 seconds. So this is a case of motion in the plane. I'm adding some questions further more to the previous video questions. You can try those questions and we can see the discussion in the next video for those questions along with some more additional questions for the revision. So the answer for the previous question is 5 seconds. Now you got already, I have given this question the last class to you. You can try this. I'm going to give you one more chance for completion of this question. You can see it's working in the next video. Uh, Here, I'm adding a new question, this one from fluids. A small solid ball of density rho is held at point a cubical container of side L, filled with an ideal liquid of density 4 rho as shown in the figure. Now, if the container starts moving with constant acceleration A horizontally and the ball is released from point A simultaneously, then you are given the options. I will also read the options. Option A, for ball to hit the top of container at end Q, A should be 3G. For ball to hit the top of the container at end Q, A should be 2G. Or even you are given C and D options, you can see the ball hits the top of the container at end Q after time T. T is either root L by 3G or 2L by 3G. We have to check that. So you can keep a pause and note down the question and try the question. We can see the next one. Two small balls of same size of mass m1 and m2 with m1 greater than m2 are tied by a thin light thread and dropped from a large height. Determine the tension of the thread during the flight. After the motion of balls are become steady, air resistance force is same on the two balls. So this is steady in the sense you can think about the terminal velocities, viscosity. You can proceed with the problem. One more question. A uniform rod of mass Kpm and length L is kept on a horizontal surface. The rod receives an impulse J at the lowest position, normal to its length as shown. Then choose the correct statement. Well asked if point P just after impact is 2J by M. Well asked if point P just after impact is J by M. Kinetic energy after impact is J square by M. Kinetic energy after impact is 2J square by M. You can try these questions. Keep a pause and just note down the questions, complete the questions. We'll see the working for these questions in the next video.